Thank you very much. Welcome, everybody. As Conrad said, this is the first, he was known as Roderick, apparently, not Arthur. So Roderick Collar. But I do appreciate there are lots of people in the audience who are actually lectured by him, so in this very lecture room. So apologies if I get some of the details wrong. Very happy to pick up some more stories and insight into the man. Okay, what I'm going to be talking about is very much influenced by some of the work that Collar is famous for. So he's primarily famous for his work in the area called Aerolasticity. And so I'm going to be talking a bit about some of his work and then how that has moved through to the design of aircraft, even through to today. I'm very much treating this lecture hopefully in BBC mode, and in the sense, if you look at the charter of the BBC, it says it is there to inform, educate, and entertain. And if I manage to achieve at least some of those tonight, I will have succeeded. So I'm going to be giving an overview, a bit about the life of Roderick Collar, talking about aerolasticity, why it's very important, and dealing some of the key aeroelastic phenomena. Also talking a bit about the analogous field of loads and the effect that loads have on flexible aircraft. And then I'll spend the latter part of the talk looking at how people are starting to use, and including work at Bristol, how we're starting to exploit aeroelastic phenomena and deflections to improve future aircraft. So that's the idea of the talk. So, Roderick Collar, when he was at school, he, via his various teachers, he was very much into the sciences and mathematics and decided that he wanted to get a job at the meteorological office. And so he then studied maths and physics at Cambridge. He opted to study physics in his final 2 years, and then seeing that as the Cambridge exams finished the day before the London University physics exams started, he decided he would go for 2 degrees, sort of thing you were allowed to do in those days. So in 1929, he graduated with 2 degrees in physics, but then unfortunately, because 1929 was the year of the Wall Street crash, there were no jobs in the Met Office. Not quite sure what the Met Office has to do with the Wall Street crash, but anyhow, so he couldn't get a job there, so he started a temporary job at the National Physics Laboratory in Teddington. That was only supposed to be for 4 or 5 weeks until people at the Met Office had then actually found him a job there. So thank goodness they didn't manage to do that for 2 years, and in that time he got so excited by aerodynamics and aeroelasticity, he turned their back on them. So he was at the NPL in the aerodynamics department for all of the 1930s. Initially started working on propellers, so working with famous names such as Glauert and Goldstein. And after about 6 months or so, he then moved on to work with W.J. Duncan, who is a famous aeroelastician with Flutter, and started to do lots of good work on tail flutter, rudder flutter, tab flutter. So again, we'll find when we start looking at what is aeroelasticity and what is flutter, you'll see that these are very important physical phenomena to be able to model. And also, in those days, aircraft were starting to get faster and a lot of problems occurred. He then moved on, though, to working on the airship dynamics of the R101, which is shown there. The R101 is famous for having a nasty crash. Lots of people died. And again, if you look at the Royal Society obituaries, which is a bit morbid perhaps, but all members or fellows of the Royal Society have a nice 20-page or so biography of their life. And for a year, Collar was working on the airship dynamics of the R101 and helping with the inquiry, trying to actually work out the dynamics of what happened just before the crash. And of course, these are the days before computers, even before adding machines. So he was doing integration and nonlinear equations using 20-inch slide rules. He also did some work on wind tunnel design. He's most famous for matrices. So he started, as I say, in the early 1930s and helped with Duncan and others to develop the matrix theory. And from an academic viewpoint, engineering viewpoint, Collar's greatest achievement was the application of what was then a very obscure form of pure mathematics, no application whatsoever, and applied that to engineering dynamics and aeroelasticity. And you could see how that is the precursor to the work that then finally developed the finite element method. Now, in those days, in the mid-1930s, if you had a 2-degree of freedom system, it would take you about 2 weeks to be able to work out the flutter speed. A 3-degree of freedom system would take you about 2 months, and beyond there, you were talking years. So again, another thing he's very famous for was developing a fast approach, termed by the Americans the British method, of how to predict flutter. All of this work is put together in a nice little textbook called Elementary Matrices. You know very well that all textbooks that have the word elementary in them mean they are by no means elementary. And this book was very, very fundamental and was continually being republished up until the 1990s. And he also, in his latter years, published a book with Alan Simpson, who was a professor here in the department, again, on further applications of matrices and engineering dynamics. At the start of World War II, he moved to Farnborough, and he was put in charge of the work on aeroelasticity. And again, we're talking about planes, so things like the Typhoon there in the top right, which were going faster. These caused more flutter problems. And not only helping to solve the problems there, he was very influential on some of the other new prototype aircraft, such as the Gloucester Meteor and the Vampire. So his work was very fundamental in helping developments in the aircraft industry. Then at the end of the war, he moved to Bristol. So I hold, as this great long job title, I am the Sir George White Professor of Aeronautics, the 5th, I guess. I am the 5th post holder. He was the first holder of the chair. He started the Department of Aeronautical Engineering. So he was employed there, endowed by the Bristol Aeroplane Company, which of course has become Airbus Filton. And there they were paying the large sum of $6,000 a year for 10 years. And he worked very closely with Filton, but as I say, built up our department that we know today. Also in 1968, which was the sort of year of all the student riots and lots of unrest, the Vice-Chancellor of Bristol was suddenly very ill, so at very short notice, Roderick had to go in and become the Vice-Chancellor. And there's a room sort of around there which is actually still known as the Vice-Chancellor's room, and I understand that was his office away from from the sort of Senate House, where he might even be able to do some engineering instead of running the university. The building we're in is the Queen's Building. You may recognize the gentleman on the left. Winston Churchill was the Chancellor of the university for about 40 years. But Collar is there watching this foundation stone being laid. But he was also, again, like these great people, very active in lots of other things. So he chaired the Aeronautical Research Council. He was the first academic to be president of the Royal Aero Society. He was a fellow of the Royal Society, which is something that not many engineers manage, and was given honorary fellowship of many societies. Also of interest that we know about the Munich air crash, where the Manchester United team were nearly all wiped out, and he was on the panel that did the second review, which effectively said it wasn't the pilot's fault that they crashed due to the slush on the runway. And also, having been Vice-Chancellor, he then sort of took up some various other administrative roles, including chairing the Southwest Regional Hospital Board. So an extremely active person, not just in research, but in other roles as well. So that's Roderick Collar. Let's start moving on to what is aeroelasticity. And this is the field that he primarily worked in. Aeroelasticity looks at the interaction between aerodynamic, inertia, and elastic forces. So I have my prop for the evening. So we have a wing. We know that the aerodynamic flow will go around the aerofoil wing, but it will cause the wing to deflect. That deflection will change the flow around the structure, which in turn will change the deflection. So we've always got this interaction between the structural deflection and the aerodynamics. And then when this starts bouncing around, we also have inertia effects as well. So it's highly important in terms of design of aircraft. And particularly things like the aerodynamics, you need to take into account these unsteady motions. So there's a number of things I'm going to go through very quickly about some of the catastrophic things that can happen due to aeroelasticity, but also as important is the response of the aircraft, because that helps very much influences the design, and particularly things like the static shape, so how many miles per gallon the aircraft will follow. So here we have this what is known as the triangle, and indeed is known as Collar's aeroelastic triangle, a paper published in the Journal of the Aeronautical Society in 1946, where he joined up the elastic forces, the aerodynamic forces, and the inertia forces in this triangle. And we see we have the subdisciplines of vibrations, of static aeroelasticity, and stability and control. And indeed, this is a magic moment for aeroelasticians, where Collar saw how these different disciplines actually came together. And Garrick, who worked at NASA Langley, described this as a map and a compass for aeroelasticians. So, Conrad mentioned that when I was at Manchester, I held the chair that Osborne Reynolds had originally held. I now find myself, I'm in the chair that Roderick Collar held as well. But there's also another famous connection with Bristol is Pugsley. You are sat in the Pugsley lecture theatre tonight. Pugsley was effectively, or certainly at Farnborough, he was Collar's boss. He started to work on the area of aeroelasticity with another guy called Roxby Cox, and was the joint inventor of the term aeroelasticity. So Bristol has a very rich tradition in this field. And Pugsley had lots of effect on the design of the Spitfire, the Hurricane, and the Lancaster. Through this understanding of aeroelastic phenomena, he was able to ensure that planes like the Spitfire and the Hurricane would not lose structural stability in flight. Now, he moved to Bristol from 1945, moved over in a sense to the dark side and went to civil engineering and worked on bridge flutter. But anyhow, so we had Pugsley and Collar, who were two of the most famous aeroelasticians ever, working here in this very building. Right, now aeroelasticity has had an effect on aircraft not since the birth of flight, but before then. So back in October 1903, you had Samuel Langley, who was backed by the Smithsonian, and he was attempting to fly what was known as the aerodrome. So this was a boat where he wasn't trying to fly it. He paid a pilot to fly this aircraft off a houseboat in the Potomac River, just next to Washington. And you also had the Wright Brothers, who lived in Dayton, Ohio, and they made bicycles. But, of course, they did lots of very good experiments and developed gliders. Langley's aircraft failed not just once, but failed twice. Unfortunately, at that time, they could have actually had some movie film of this. They didn't. That's the only known photo of this plane collapsing. And what you can see is the rear lifting surfaces failing. Now, it's supposed that this was due to what is called divergence. So this is the aerodynamic loads So it's like you're pulling a spring and eventually the spring breaks. You've pulled it too much. The aerodynamic forces overcome the structure. We know that this is because the wings weren't stiff enough, because somebody called Samuel Curtis rebuilt the aircraft some 10 years later. The Wright brothers were very litigious. They had invented the aeroplane. Anybody else who tried to make one owed them royalties. And there was a lot of legal battles for 10 years or so. It's probably why the Wright brothers aircraft in the end got superseded, because they spent too much time in court rather than developing their aircraft. So Curtis rebuilt the Flyer from Langley, but with stiffer wings, and it flew. In the European courts, they sided with Curtis. In the American courts, they sided with the Wright brothers. So it was much easier to develop aircraft then in Europe. But this also has other effects. Now, I don't expect you were thinking you were going to see a windmill tonight, but if you look at the classic, Dutch landscapes with cows and canals and windmills on it, if you look at the pictures from the 15th century, you'll find that the main spar, so this main bit running down the windmill, the wings, is at the midcord, so in the middle. And then through the centuries, you find that the main spar moves forward to the quarter chord. Now, aeroelastic theory will tell you that's because you put the spar on the quarter chord. Of course, Dutch windmill makers knew nothing about aerodynamics or aeroelasticity, but what they knew was by trial and error that if you put this spar further to the front of the chord, your windmill was much more likely to survive big storms. This phenomenal divergence actually got its name from Anthony Fokker with what was a plane called the DV-8, or the D-8, which was a World War I aircraft, which with the wing, so it's a monoplane, and it's got two spars running down there. And for whatever reason, the German Air Force decided to reinforce the rear spar. Okay, so that's the front, that's the trailing edge, and what they then did was rebuild this spar to be much bigger, and unfortunately then several planes crashed. And of course, when you get a brand new aeroplane, you let your top pilots go and fly, and there's a lot of disaster, and Anthony Fokker then realized by putting weights and looking at how the wing deflected, that what they'd effectively done was moved the flexural axis further aft, and therefore that caused a larger moment due to the aerodynamics, and that caused the failure. So that's the first time that divergence was actually identified and given a name. And meanwhile, of course, before this, about a month after Langley's pilot ended up in the Potomac River, the Wright brothers flew. And notice that they didn't have ailerons. Again, ailerons were invented by Curtis because the Wright brothers used wing warping. They had the pilot in the cradle who could, by moving about and a set of cables, could make the wings twist, and they used that for roll control. Remember that, because we're going to come back to wing warping 100 or so years later after the Wright brothers. Time to wake you up. Let's actually see what Flutter is. There's lots of videos on YouTube and the like. Most of them are in slow motion. This is from NASA Dryden, I guess over 10 years ago now. What we've got here is an F-16, and it's got a model about 1.5 meters long sticking out beneath it. The excitation there is purely due to the air turbulence. And what the pilot doing is slowly descending. It means the Mach number's going up. The question is, would you stop the aeroplane in time?
Terminate. Knock it off. We lost it. We lost the tip.
Von Karman, some fear Flutter because they don't understand it. Others fear it because they do. My students and people would know that today I was sat there putting this talk together making some finishing touches. And people who know me know that if I'm going to a meeting, that's what the aeroplane's for, is to put your presentation together. About 5 or 6 years ago, I was flying across the Atlantic, and the next day I had to be in Paris, and I had to give a talk about Elasticity. So, of course, I was putting together a talk, and I was going to put that video in it. And the people sat next to me said, "Oh, that looks very interesting. You're doing a talk about aeroplanes. And, have you got some videos? Can we look at your videos, please?" And I said, "No." And they spent about 5 minutes saying, "Oh, please, please." And in the end, I said, "Yes, okay, but with a health warning, you don't want to watch this." And of course, they watched it and were a little bit horrified and were saying, "Please, can you promise for the next 7 hours that that's not going to happen to the wings?" But of course, we understand Flutter pretty much nowadays, so we're able to design aircraft so that doesn't occur. But it's that suddenness of the instability that I think is the main problem. Now, how does Flutter occur? Flutter occurs because it extracts energy from the system. So we talk about this thing called modes, where, okay, so that's the first, what's called a symmetric bending of an aircraft, and that may couple. So each of these motions is going to affect the aerodynamics, and there we've not only got an asymmetric behavior, but we've got twist as well. And the system behaves in such a way as to extract energy from the system. So again, this is another Flutter doesn't result in failure. Okay, so that's they slowed the plane down, a nonlinear phenomena stopped it. But what we can see here is that we get a twisting mode, and that is combined with probably the second bending mode, so we're going to get like an S-type shape. Sure, it wasn't very... Well, it's an unmanned little RPV, so nobody was harmed, but I'm sure the pilot was worried about seeing that thing vibrate. But good as an explanation as to what's Flutter. Okay, let's move on to another aeroelastic phenomena. There's lots of famous aircraft that have come out of Bristol, but I don't know how many of you know about the Bristol Bagshot. Okay, that's first flown in 1927, and they said the first flight was short, which is always a bad sign. And the pilot was increasingly worried about writhing moments of the wing that were large and alarming and being unable to control the aircraft. And so it was transferred to the Air Ministry and then was broken up for scrap. So it flew about 3 or 4 times. So not the most successful aircraft to come out of Filton. But it's the first case of control reversal. Now, control reversal, again, is an effect where if we have a wing, and so we have a lift and we have a moment due to lift forces, but if we apply the control surfaces, we actually create more lift, but we also create an anti-clockwise moment. And what that does is not only creates more lift, but then causes a reduction because the angle of attack reduces. And at some critical speed, these two effects cancel each other out, and we get what's called reversal. And in fact, if we go beyond that speed, the control surface has the opposite to that required. So, but don't take my word for that. Let's see a film starring Rolf Richardson and Anne Todd. So this is talking about the first de Havilland aircraft.
Heavy business by reversing the controls. Anyway, we're going to try. I won't be a moment.
So they had problems trying to break the sound barrier in that the controls became very heavy. At least one pilot, in fact his brother, who was then married to Anne Todd before she married him in the film. It's a bit of a tearjerker.
All right, here we go.
Trying to figure out. But
increasing speed. 9-4. 9-5. Mustang. 9-6. 9-7. 9. No, shut up and go. I'm putting the stick forward. He's coming up! Coming back! Pulling on the ball! I did it! I did it! One four to tower. On fourth run, Mark Peter showed 1.01.
I get annoyed if the students don't know what control reversal is after I show them that in my Elasticity lectures. Apparently, of course, the Americans broke the sound barrier in 1947, but kept it sort of reasonably quiet. And apparently, the US president actually then brought in the British ambassador, saying, "Well, why is this looking as if the Brits have broken the sound barrier?" But it's all, well, I guess it's not. It's an Ealing film, isn't it, rather than one from Hollywood. Right, I digress. Let's get back to the main issue. Right, okay, that's control reversal. Other things we're interested in are things like what's called limit cycle oscillations, where either we have a structural nonlinearity or we have shocks. And what this is a F-16, and what you can see is due to the aerodynamics interacting with the structure, we get this little oscillation, which, okay, small oscillation there, but it can limit the different combinations of stores that military aircraft can use, can cause problems with weapon aiming, discomfort for the pilot, and also extremely difficult to predict. I saw a whole series of tests about 5 years ago where they were looking at different combinations of, let's call them stores, and flying the aircraft and then seeing how far into LCOs they could go. Still can't really do that computationally at the minute, and you're talking a 350-day test program at that time was about $200,000 an hour to do, so big costs. Also things like stall, if the aircraft wing deflects too much, it loses lift, and then we can get, so basically the wing is twisting, losing lift and bouncing back. So that's some work from a former PhD student of mine in Liège in Belgium. Okay, we're also interested in loads. Okay, so loads are what helps design the aircraft. We have to consider many design cases and look at loads due to maneuvers, due to landing, braking, turning, and also gusts and turbulence encounters. And we have an equivalent triangle, which is now the loads triangle, again joining our aerodynamics to our elastic forces, to our inertial forces, but now we have ground loads, equilibrium maneuvers, and gusts and turbulence loads in the middle. So, right, 2 seconds, I have to change video. So if we look at, so this is from a European project from, some years ago. Right, there we go. Right, okay, so we have a wing, we have a wind tunnel, we have what are called gust vanes that can move, and we can see here that when the vanes move, we can see how that affects the response of an aircraft. So the sort of thing when the pilot tells you to buckle up, that's the sort of thing you want to be able to predict and work out what the loads are. And of course we can move away from a wind tunnel model, and then same thing. So this is called the URAM model. This is a 22 feet span aircraft, so it's a real wind tunnel model. Again, same thing, we have these gust vanes and we can look at the loads that is causing on the aircraft. So we're interested in being able to compute those loads, and that helps us to size the aircraft. And again, we want to make sure, again, an aircraft is unique, that not only must it be strong enough, but we also want it to be nice and light. So here's some quite famous examples of aircraft. These are apparently real. You don't want to know about that if you're sat in your aircraft. And similarly on this one as well. Ooh. So we've always got this trade-off between the strength of our aircraft and its weight. It's quite easy to make a very heavy aeroplane that flies but doesn't sell, hasn't got particularly good performance. But if we want to make it nice and light, we've got to make sure that we get our calculations correct. So what we've seen is most aeroelastic phenomena are desirable. So traditionally, designers have just taken a penalty and said we're going to have a stiffer, i.e. a heavier structure, and we're going to eliminate our aeroelastic effects. But of course that means we get heavier weight and then more drag. So, half an hour in, the exam question for tonight. How can aeroelasticity benefit future aircraft designs? Okay, so I'm sure you're all aware of this sort of plot where we're plotting here engine fuel consumption and also the fuel burn per seat compared to the 707 in 1960. And we can see, yes, the aerospace industry has made big gains, but these curves are flattening out. So the question is, have we optimized our conventional configuration with a tube and wings and engines on pylons as far as that can go? And again, we've got all these typical growth forecasts saying there are going to be many more flights, particularly in the Far East. There's various initiatives. There's something called Flight Path 2050, which is some very extreme targets set by the EU. Quite whether that is a typical 707 in the late 1950s, I don't know. But it certainly doesn't look very environmentally friendly, does it? And what we're looking for is not just environmentally friendly aircraft, but we're also looking at better certification design methods. If we start moving to non-conventional configurations, can we do that quickly and safely? The Americans have a similar set of goals as well. So again, we're looking at less noise emissions, reducing the drag, improving our propulsive efficiency. And in 20, 30 years' time, are we going to start seeing, high aspect ratio wings, forward swept wings, blended wing bodies, lifting fuselages, or even joined wings? We don't know, but eventually some manufacturers are going to have to take the plunge and move into some of these new technologies. Now, apologies. Stephen Hawking's book, A Brief History of Time, he says that every time you include an equation, you lose half your audience. So half of you can walk out now because I'm going to show this equation several times, but it's the same equation. Traditionally, aircraft are designed at a single point in the envelope. So this is speed against altitude, and you pick a design point. But everything is regulated by this thing called the Breguet range equation. We won't go into the details, but what it tells us is there's only three things we can do to make an aeroplane have better performance. So either better aerodynamics, so L upon D, less structural weight, so that's contained in this term, and then better engines. Sorry, Conrad, I'm not going to talk about engines tonight. Next year we'll get an engine speaker. Okay, so again, an aircraft is a compromise. From a technical viewpoint, you may be wanting to tie your weight against your aerodynamic performance. One of the things that I've really noticed or learnt about since working closely with Airbus is the financial viewpoint. You may design an aeroplane which is the absolute Rolls Royce in terms of environmental efficiency, but if it costs an awful lot to buy and costs an awful lot to run, Mr. EasyJet is not going to buy it. So how does aeroelasticity affect the range equation? Well, if we can, rather than just worrying about a single point in the flight envelope, if we can actually use some aeroelastic design or various methods, we can actually get our desired shape throughout the flight envelope. We can use things like Flutter suppression. I'll show some videos of that later on to reduce the weight. We can alleviate loads, again reducing weight. And we can start using what are called nonlinear devices to improve upon our linear performance. And another area, which I'm not really going to touch on at all, is looking at sensitivity and what's called uncertainty analysis. So this helps with our design. So, again, if we're using aeroelasticity properly, we ought to be able to design over the entire flight envelope, and then we can do this in a robust sense. So whatever the price of fuel, we can still have a design which is very robust. And it also helps us with some of our design questions about, say, the uncertainty of the weight against the actual weight. And we've always got this trade-off. Again, despite having very good computers nowadays, there's always more computing that we need to do. How can we get enough accuracy but get it as fast as possible? So I talked about how we're going to use aeroelasticity. Up to about the year 2000, we just basically, aircraft were made, and then we took this hit of having to make them heavier to try and avoid things like flutter or divergence, or to get the right shape. What we're trying to now do is operate in this part of the envelope. So actually, can we use aeroelastic concepts to get some benefits? So I'm going to spend the last 10 minutes or so of this talk is looking at some possible future technologies. How can we exploit structural flexibility? And there's a range of passive and active approaches. Some of this is from work ongoing at Bristol. Other work is from elsewhere. But a guy at Wright-Patterson Air Force Base, Ed Pendleton, came up with this phrase that it's back to the future. So I mentioned the Wright Brothers 110 years ago warping their wings. In a sense, they were using the aeroelastic effects for their benefit rather than fighting against them. It's not new, of course. Lilienthal had similar devices on some of his gliders in the 1890s. So one of the first things I talk about is using composites. So rather than having a metallic structure, we use composites, but we exploit their anisotropic behavior. Now, forward swept wings are very good aerodynamically, but we don't see many planes that are forward swept wings. Okay, there's a few low-speed gliders. The X-29 in the 1980s, and there was a Sukhoi aircraft that was a copy. And for those old enough to remember, Thunderbird 2 also has forward-swept wings. But there's some work being done there by, Paul Keeley, but particularly Olivia, collaborating with myself and Paul Weaver. And that's saying not just to use the composite, but to be able to change the direction along the wing. And what we can then do is to couple the bending and the torsion behavior so we can improve the flutter speed, we can alleviate loads, and we can try to optimize the flight shape. So we really are trying to cut the grass and kill the weeds. So, and you can do things like look at this at a local level for buckling or trying to improve the aileron performance. So we talk back to roll reversal, or look at this in a global sense. And this work is showing some great promise, also directly from Olivia's work, but where we plan to go next. So here's, again, this is just a simple ply. These lines there show the angle. So you can see, like with the red lines, how the fibers are being moved up and then along and back. And it's a big optimization problem. But again, some of the simple wings that we've looked at, we've increased the flutter speed by 13% and reduced the gust loads by 24%. Of course, there's manufacturing problems. Airbus talk about aiming for 50 or 60 new A320s every month. And at the minute, here at Bristol, we have a machine which is like an upside-down sellotape dispenser, and that does about 5 centimeters every half a minute. So we're not quite up to 60 pairs of wings a month. It may get there in the end, I hope. Another example, again, working with Airbus. There's a big drive at the minute for looking at folding wings. Okay, so if you have very longer wings are good aerodynamically, it reduces the induced drag. But if they are too long, you get charged more money to use the airport. So the next version, the 777, is reputedly going to have wings that fold. So not in flight, but when they land, these wings will fold up, and it means that you'll fit into the parking gate and won't incur such any large charges. So what we've been looking at is, well, what can we actually do? If you've got a fold in the wing, can we actually use that? So when we get hit by big gusts, by having some sort of spring mechanism there, can we use this folding wing to reduce loads? And initial studies have shown that this is very promising. So this is a bit of a complicated graph. The dotted line, black dotted line there is the baseline model, and then what we've done is increase the wings by 20% span. And then by changing the spring stiffness, and also by changing the angle of that hinge, we're able to get almost the same load. So that's the response to a gust, almost to get the same loads, even though we've increased the span by 20%. So again, watch this space. This is a very exciting new technology. So potential to reduce the loads, and also it means we can park these long wings in the, about to say, the car park at the airport gates. Okay, another area we've done lots of work in is what's called morphing aircraft. If you dial up morphing, you get this picture there. That's really from Disney. A lady called Anna McGowan, who works for NASA Langley, who was told by her boss that, right, you're running this $100 million morphing program, but you've got to go to the Senate next week to argue for the money. We're sending a man from Disney tomorrow to make a video for you. And there's this wonderful video going from an Eagle into this morphing aircraft. So everyone thinks this is a top secret NASA configuration. No, it's not. It's the man from Disney's idea of morphing. But there's other things we can do. So from a military viewpoint, you may have an aircraft which, we can loiter with a high aspect ratio wings, and then like some birds of prey, you bring your wings in, and you're highly maneuverable and able to meet your mission by being maneuverable. Again, things like performance morphing. So rather than changing the plan form, what can we do to the wings in terms of the stiffness or the camber, and we can improve our performance. Again, it's not new. Concorde, in a sense, had morphing because the nose drooped. Tornado wings folded back when they went supersonic. And there's other work around. This is from Virginia Tech, looking at wings that expand in span. Again, other mechanisms for changing, a bit like a seagull. So the wings are out wide and then move up when the seagull wants to become maneuverable. So we've done lots of work looking at adaptive structures. So rather than using lots of piezo or devices to twist the structure, let's do something with the internal structure and use that to change the shape. So one of the most successful concepts, perhaps the easiest, if we have a ruler that's like this, it's very bendy, turn it through 90 degrees, and it's very stiff. And so what we've done is apply that to a series of aircraft wings and other configurations. So here we have a structure that has two rotating spars. Here's the first prototype we made just before I left Manchester. So we've got two rotating spars there joined up with various motors. Takes about half a second to go from maximum to min rotation. The key thing to this is you've got to be able to transfer the load. If you just rotate the spar and don't attach it, it ignores the spar that you're moving. Okay, so in this first example, we're going to go from, that's just out the tunnel, or that's wind off anyhow. The next bit of the move, I never learned to speak long enough with this, we'll then go to the wind tunnel. Come on. And there we go. So, okay, this is about, 15 meters per second. We can see our spars there like so. We can see when we twist them that we're able to get about 4 degrees of twist, and for a meter-long wing, about 8-9 centimeters of bending. And we developed that a bit further in a recently finished EU project, where again, in a much better mechanism for doing this. But what you do, this is not active. It's not aiming to change a shape in milliseconds. What you're doing is slowly changing the shape over the flight so your wing takes the optimal shape throughout the entire flight. Very efficient, works very well. And you can do the same thing with torsional stiffnesses. So rather than having a conventional fin, we have here an all-moving tail just attached by a single spring, but we need that for various reasons, things like crosswinds, and also because we haven't got a rudder, we need to find some way of changing that stiffness. So here is a tail from the big URAM model I showed in the wind tunnel in Moscow. So work at Manchester was looking at various ways of changing the stiffness. Here we have a simple pneumatic device. It doesn't have to be pneumatic. There's various other mechanical means. But what it means is that you can, with the airflow, rather than moving it, you just change the stiffness there. Okay, we could probably do a bit of damping, but we're able to change the orientation of that wing purely just by changing the air pressure. We're running out of time, but I could tell you a big saga of when somebody from Manchester Airport rings you up and says, hello, I'm from Customs at Manchester Airport. You have a wing here from Moscow. And in days gone by, you just said, I work at a university. It's like if you're an American, you say, I'm English. You know, it gets you out of lots of trouble. But no, because the Russians said it was worth 30,000 euros, and it was made of about $200 of plywood of that. I had big problems and nearly got summons by customs because I went on a holiday rather than sorting this out. Anyhow, back to our URAM model. Again, this is our 22-foot span model in one of the big wind tunnels at Sagi. And if we go back to this video and just check my numbers. So what we can now see is almost the proof of the pudding of that to there. Okay, so what we've now got is this full URAM model, but now with this active aeroelastic vertical fin. And what we're going to see, now you wouldn't fly the aircraft like this, but just to demonstrate that by using a particular arrangement, we can actually move the tail, again, just by changing the stiffness of the spring at the bottom there. Okay, we're getting there, right, so. And then the other thing I think is going to come in at the minute is flutter suppression. So here's some work I did with colleagues at Liverpool, where we're using an active device. Okay, this is using piezo stacks. And if we can increase the flutter speed, it means we can then reduce the weight, make the aircraft more flexible, and still make sure that the aircraft doesn't flutter. Quite how the certification authorities or even the passengers are going to cope with that, I don't know. Okay, but here's a gust. So, oops. So what we've got here in this wing is our wing model. It's a heave pitch motion, and we're going to put a pulse into there. So it's going to move. The first time the system is off, the second time is with the closed loop. And you'll be able to see how, if I press the right button, we get motion. Okay, so we're looking there. So tap it. Nothing much seems to happen. Turn the system on, bash it again, and you saw that control surface moving. So that's the actual time histories there, and you can actually see that there's a large amount of extra damping, which is good for avoiding flutter just by using that closed loop control. But this is all sort of toy stuff, I guess, compared to what some of our colleagues over the Atlantic are doing. And so I've got 2 more videos left. So this is talking about active flutter suppression.
There is a dragon that lives in the air. It lurks where aerodynamics and structural dynamics collide. And it is called Flutter. Flutter is a result of aerodynamics forces and structural dynamics coupling and going unstable. Flutter can be catastrophic to bridges and aircraft alike. In 2005, Lockheed Martin initiated an independent research project to validate its flutter modeling techniques and to investigate the possibility of active flutter suppression. To minimize cost, 5 very lightweight expendable RPVs were designed and built. These vehicles were called Body Freedom Flutter Vehicles, or BFFs. The success of the active flutter suppression system demonstrated on the BFFs led to an AFRL contract to build and test 2 more. The MAD program was initiated by AFRL to mature active flutter suppression, to allow longer, more flexible wings and lighter weight structures that'll allow future aircraft to fly higher, faster, and further than before. The X-56A has been designed to perform other types of research as well. The X-56A incorporates an open architecture vehicle management system computer, an expandable data acquisition system, air data flight test boom, 2 80-pound class JetCat small turbine engines with electrical power generation, excess power and volume for future testing, and a ballistic recovery system parachute to protect the valuable system during risky flight tests. The MAD program is delivering the X-56A MUT vehicle as a complete research system, which includes the ground control station, simulation, system integration lab capability, and a vehicle transportation and storage trailer.
Clear to test point 7.5.
Roger, 7.5, increasing speed to 95 knots.
Knock it off, knock it off. Okay, that verifies our flutter speed is 95 knots.
Flutter speed is 95 knots. Clear to test point 7.6. Flutter suppression on.
Flutter suppression on, cleared 7.6, accelerating to 150 knots.
95 knots, 100 knots, 105 knots, 110 knots, 115 knots, 120 knots.
We are flutter free. I showed 3 modes suppressed.
So there we go. I have colleagues here at Bristol who are working on a sort of European version of that project, so I hope they beat the flutter barrier soon. Okay, so I hope that you've enjoyed this evening. I hope Roderick Collar will be pleased to see there's still a lot of aeroelastic work going on at Bristol, but we've seen how aeroelasticity has had a major influence upon aircraft structural design. We've also seen that most of the effects of aeroelasticity are negative. Usually that has meant we need extra weight, but I've hopefully shown that there are some possibilities via current research here and elsewhere in the world where by using aeroelasticity beneficially, we're very likely to see this technology appearing in future aircraft designs. But it's not over yet. Fight now. If we get these Channel 4 and Channel 5 programs of the 100 greatest this or that, well, if there was a program on the 10 greatest Flutter videos, this would be like Bohemian Rhapsody, because it would always be the winning version. And I cannot give a sort of overview lecture on aeroelasticity. Liz, you will have seen this talk before when I was at Liverpool. This is your prize for coping with me talking to you for the past hour. If I can find the go button. Right. So, thank you all for listening. I'd like to acknowledge funding from Royal Academy of Engineering and Airbus. And also, that's just a selection of current and previous researchers, some of whom's work been included. But it's one of the great joys of working at the university is being able to work with such fantastic youngsters full of lots of good ideas. And I still don't consider I really have a real job, but don't tell the head of school sat there at the back. Right. Okay, with that, I'll say thank you very much. Thank you. Thank you very much.